Luiten to give his second of his 4 lectures on metrology, and I'll just fill for a second while he gets the microphone. And ready. Okay, ready.
All right, so we have to turn the lights down, or are we all good like that? So, if you didn't believe in the last lecture that we should only ever measure frequency, now you take the advice of the Nobel Prize winner. Shavlov here's advice to Ted Hench, who's the guy sitting in the right-hand corner at the front in a Munich beer garden. Never measure anything but frequency. Now the nice thing I like about this photograph is that the two people that went on, this photograph was taken in something like 1999, the two guys that went on to share in the 2005 Nobel Prize, which is Jan Hall, who's in the front left-hand corner, and Ted Hench, as I said, is in the front right-hand corner. Neither of them have a beer in front of them in a Munich beer garden, whereas the other two guys who haven't won a Nobel Prize have a beer in front of them. So there's your advice for the future.
Give up your Nobel.
That's the price. For most of us, it doesn't matter anyway. So these guys face this challenge of how can you make ultra good measurements of optical frequencies, which at that time, was basically a total nightmare problem that filled essentially like a good part of an entire building in a very complicated harmonic chain technique if they wanted to make a measurement of a single optical frequency. And these two together essentially solved the problem of how to actually do that in a simple tabletop manner that even in the Australian context we can have a couple of these devices in our lab to make optical frequency measurements. So what is the solution? And once again, I'm going to engage your ears because we're going to use like audio analogies of what's going to go on optically in order that actually makes this system work. Because I think that if you listen to it in this strange world where time's slowed down by 1 billion times, I think it makes it very clear. So, and I'll use as a concrete example the values of things that I'm putting on the slides here are in fact those that apply to our situation in our lab. So we can generate a short pulse of light which lasts for just 40,000 trillionths of a second, or 40 femtoseconds in the language of the field. And so let's listen to this if time was 1 billion times slower. Actually, I lied to you, that's the wrong order. That's a 1 picosecond pulse there. So now let's listen to the 40 femtosecond pulse. So I think if you compare the two have the same carrier frequency, but I think your ears can hear the difference between the two. The first one sounds a lot more acoustically pure, and that's actual real life, that's the Fourier transform limit. It's not just your ears playing tricks on you. Short pulses have intrinsically ill-defined spectra. And so our 40 femtosecond pulse, if we look at the spectrum of that pulse, it essentially looks like it covers up a fair bit of the optical spectrum, like something like 50 nanometers in width, centered in our case at something like 800 nanometers in the optical spectrum. So it's intrinsically frequency broad. And why is that? Well, essentially because it only exists for a few cycles here. So now I hope you've all got confused feelings because you're thinking, he said that we're going to make very precise optical frequency measurements, and I'm going to use this as a tool, and this pulse is, of course, is poorly defined in frequency, so it's strange that I can use this pulse to make precision measurements of frequency. So we obviously need to use some other trick. And what's that trick? Well, that trick is to take that pulse and actually stick it inside an optical cavity and make it do a loop around. One of the mirrors is partially reflecting, so we hear the pulse coming out in a regular way on the output. So how is this going to solve our issue? Well, if instead of looking at the Fourier transform, instead of looking at the Fourier transform of a single pulse, if we look at the Fourier transform of a whole pulse train, which has got a separated by something like a nanosecond in our case, because this cavity is 15 centimeters long, then the Fourier transform of that repetitive pulse sequence is in fact a repetitive structure in frequency space as well. It's a whole bunch of delta functions which have an envelope which corresponds to the 50 nanometers I spoke of before, the pulse duration of a single pulse. But there's this internal substructure inside this broad structure which reflects the repetitive nature. And so if this is 1 nanosecond between the pulses, then essentially it's 1 gigahertz between the sticks. Well, that's starting to sound interesting because that looks like a ruler in frequency space. It looks like I've got a whole bunch of marks on my ruler that are exactly 1 gigahertz apart. And this is starting to look like a solution for how I can measure, how I can make a measurement, say, between two optical signals which are separated by a substantial distance in the optical spectrum. I can just count how many sticks there are between them and figure out how far apart they are, which is already a big leap forward because nobody could do that prior to this work in the sort of late 90s and early 21st century. Okay, so the devices that actually produce this sort of thing look something like this. They sit on an optical table in my lab. So there's a titanium sapphire crystal here, and the pulse circulates around in this relatively complicated optical environment. It's going to bounce off 6 mirrors and pass through the crystal. And it turns out that there are various dispersive effects that go on inside this cavity due to the interaction of the light with the various optical components. But in addition, the physical length of this cavity is not exactly stationary, right? Because there's vibrations and the air rolls through it. And so instead of the cavity being exactly 15 centimetres long at all times, which we need to have exact repetition between those pulses, is going to fluctuate. So we need to control the length of this device. We also need to think about perhaps controlling dispersion fluctuations inside there in order that that comb of frequencies is held exactly constant. So I want to show you visually what does it look like when, if those parameters, the length of the cavity and the dispersion are fluctuating. So here's what happens if we stretch the length of the cavity. Like what do the modes, so this is a picture of what those modes of the combs, some little schematic view of them, what do they look like? It looks like the comb itself is being stretched when I stretch the length of the cavity. Of course, it happens in antiphases, and I make the cavity shorter and the frequencies get further apart. But nonetheless, I can still express all of these, the spacing between these cone members are all held. They're all the same, but they're all just stretching in sympathy with the cavity. So how do I go about controlling that? What I do is something very, very simple. I let the pulses come out of the cavity and I detect them on some sort of fast detector as shown up here. And then I compare it to a really good clock so that I make sure that the time between the pulses is well controlled in terms of that other clock. And then I actively control the length of my femtosecond laser to hold all of these at a well-defined separation. And if I do that, then I end up with a comb that's got fixed interval spacing. And in fact, now that we're all experts from the previous lecture on considering noise and things, we can see here's the fluctuation in one of these femtosecond lasers due basically to air and vibrations and things like that. It's got a very, very steep spectrum, so there's lots and lots of fluctuations at low frequency. And once I engage all of my fancy locking systems, I can suppress this down by something like 100 dB or something, or 10 orders of magnitude. And you can express that in another way. Instead of expressing it in the spectrum as I just did there, I can also, as we saw, I can make measurements of stability in 2 different ways. So here it is expressed in terms of the Allen variance. So where before the sticks were moving around about a megahertz between the spacing between those, and as we go to longer times it gets worse and worse because of drifts and things, which is exactly what the spectrum tells you about in the previous slide. And once I engage all of my control systems, I can suppress the spacing fluctuations down to below a hertz. So you can see that, in fact, there's 6 orders of magnitude of suppression in the frequency fluctuations. So that means that even though all of these sticks are up at 3 or 4 by 10 to the 14, 300 terahertz frequency, the spacing between them is fluctuating less than 0.1 of a hertz over timescales of a second. So you can see some of the amazing precision that you can build into these frequency metrology systems. Well, there's another degree of freedom in that cone that I haven't controlled yet, which is even if I kept the spacing fixed, the whole cone could translate in frequency space as well. And this was really, I think, the key breakthrough that led to the Nobel Prize, was how to measure that translation of the cone, that uniform translation of the cone, which has its origin in fluctuations in the dispersion inside the laser cavity. So that even if I control the length, you'll still note changes of this type of magnitude. And this was the breakthrough of Hench and Hall, was essentially to come up with a technique, the philosophy of how you can do that. So what they said, and I think it's a pretty cool idea, is that they said, let's take a couple of these cone members down the end here and stick them through some nonlinear crystal so that it doubles their frequency. So the lower part of this translating thing is the cone shoved through a doubling crystal. And of course, because these have been doubled, these translate twice as fast as the fundamental cone. And if we compare these frequencies of these fellows against the ones up here, then of course there's going to be a shift between the two of them because this one's translating twice as fast. So if I lock it at some particular point like now, where they're in exact harmonic relationship with each other, then in fact, if you think about it, it means that all of those sticks are in fact on the exact harmonics of the repetition rate. And so everything will be good. I can detect the difference. I can actually detect this so-called offset frequency in a reliable way, and I can stabilise it by changing the dispersion in the cavity, which I can do actively by changing the pump power into the laser. And the world will be a good place because now my cone will not only have uniform spacing, but will also be fixed in absolute frequency space, which means for the first time I can make frequency measurements in the optical domain with absolute accuracy. Well, there's a little trick that I sort of covered up here. But although that sounds pretty easy, we'll just take this part of the cone and double it. This relies on the cone existing at two places in frequency space that are a factor of 2 different in optical frequency, so like red to blue. And as I showed you, that fundamental pulse that comes roaring out of the laser that's 40 femtoseconds long only covers something like 50 nanometers. What we want is that cone of frequencies to cover a full octave of frequency space to have this technique work for us. So how can we go about that? And this is a sort of a technological solution, which was this so-called photonic crystal fibre technology where one can launch a pulse into the central core, a defect in this photonic crystal. So there's a micrograph across a piece of optical fibre. So here it is at lower resolution, and we can zoom in and see the central core in here. So this is exactly the fibre we're using in our lab. So if we launch a pulse into this central core, and the function of the photonic crystal is to do 2 things. One is it provides much tighter transverse confinement than occurs in normal optical fibre with much bigger cores. But the second thing that it does is that it modifies the natural dispersion that exists in silica in order that instead of the pulse spreading out as it propagates in the silica fibre, it stays stuck together. And that has the advantage that the super high optical intensities stay high as that pulse propagates through the fibre. And then that engages a whole bunch of non-linearities, which result in the spectrum, which starts off at a narrow 50 nanometers or so, broadening out so that in our case it covers from something like 400 nanometers in blue to 1600 nanometers where our detectors run out and presumably beyond there. So we've more than covered a factor of 2 in spectrum. So that does correspond to making the pulse extremely short, but it turns out that because of all of these higher order dispersions, you can't really put it all back together, so there's a whole bunch it's not a Fourier transform limited pulse anymore after it comes out of it. So we engage that control, and so it turns out the fluctuations associated with this translation of the cone, apart from the stretching, are about the same level, also about a megahertz. And once we've engaged that control, the fluctuations due to translation are down at the millihertz level, or parts in 10 to the 18. So this cone is really a device which can work at the absolute limit of whatever your other clock is. So we can translate the output of any clock, whatever frequency domain it falls in, up into the optical domain. So since I can't take you all to my lab, I thought I'd show you a little video that shows what the sort of magnitude and complexity of this thing is, with some nice music. So here you can see we'll see the actual supercontinuum process going on in real life. So we're all learning how to play with the zoom on the video camera. So here's the internals of the titanium sapphire laser. So you can see my lab's not very clean. in fact this thing over here is a giant acousto-optic modulator. It's also here, which we use to modulate the output power of our big green laser, which is pumping out our femtosecond pump laser, so that we can change the dispersion with a fast response speed. And in a second we're going to get to the exciting part, which is, so now John McFerrin is adjusting up this mount, which is going to inject the pulse of light into the fibre. So this is the output spectrum from the fibre. So what started off as a narrow spectral feature can be spread right across from the, what actually in real life looks from blue to the red. And as he's adjusting the input power of the fibre, you can see the spectral shape of the output of the fibre actually changes around quite a complex shape. And here we can see the scattering from the side of the fibre. So as he's changing the power, you can see the scattering shifts from red to green. It shows the spectrum as it travels through this fibre is actually broadening out. No, it's too nice, you can't stop, can you? But you know, what can you do? So here's the proof that it really works. So what we did in this experiment here is we used our frequency cone technology to connect the optical and the microwave domain. And what we've got down the bottom is we built 2 microwave clocks, which are based on this cryogenic sapphire technology that we haven't got time to talk about. And we measured the frequency difference between those two. And on the grey trace at the top, we built 2 optical clocks, and we measured the frequency difference between those two. And then we compared the optical to the microwave clock using the frequency cone, and we did all that simultaneously. And I think you can see that the optical to microwave trace exactly, I mean, most of the noise is coming from one of the optical clocks, and there's a little bit of high frequency noise that's come from one of the microwave clocks. So it really does work. You really can translate from one side to the other. And there's another example of the amazing measurements you can do here. This is some work by Harold Teller from a few years ago. So what he did is he took some sort of optical standard over here, and he doubled it in some nonlinear crystal, so that you'd expect that the frequency here and here differ by a factor of 2. And then he put it through his whole femtosecond clock scheme, which is a little bit more complicated. He's done something fancy so he can avoid stabilising that so-called offset frequency. And the net result is that he basically measured the ratio of this frequency to this frequency, which we expect to be 2, right? And here he measured it, so I'm sure you've never seen 2 measured more accurately than that, right? 1 part in 10 to the, well, a little bit better than 1 part in 10 to the 18. That's quite nice.
Now with this new treatment for...
Well, let's leave that out. Would have been funny. We're running out of time. So the other thing I wanted to point out to you is that you saw all the stuff that was on that table for the traditional type of frequency cone built on titanium sapphire lasers. Well, there's another way that you can build these systems these days using fibre laser technology. And so we've done something exactly like that. So here's our new frequency cone system, which is basically a little portable system. So essentially we have a femtosecond laser based on fibre technology and a doubling crystal over here. And then it turns out, you can't see it, but there's a fibre stretched between these 2 microscope jet tubes. And this fibre does something for us. It's very tricky, but essentially allows us to do the whole frequency cone setup in one stage. And I'll show you in a second what that is. And then there's a detector over here, and that's your entire setup. And that's portable, and it's allowed us to do an exciting experiment, which I'll show you in 2 slides' time, because you don't need all of the paraphernalia that you saw in the previous one with this much more simple setup, and you just turn it on and it works. And it's much cheaper as well. So we've got some of this other photonic crystal fibre that's a little bit different. This one's got like this strange hexagonal hollow core in it, and by accident we found that if you launch these femtosecond pulses into these intersections, in this hexagonal structure that surrounds the core, then you see all these beautiful colours depending on which one you launch into. So this is a very narrow spectrum, something like only 5 nanometres wide, at 780 nanometres is what comes out of the laser. And when we inject it into the fibre, we can see this beautiful green colour, or yellow colour, or purple colour that comes depending on where you inject it. So that allowed us to do a really cool trick, because as I showed you, the laser generates its fundamental spectrum at 1500 nanometres, and it goes through the crystal and generates 780 nanometers a second harmonic, which we then launch into this fibre. But simultaneously, that little crystal that does the doubling does a little bit of tripling as well. And the triple of 1550 is around 520 nanometers. And it turns out this green colour that we can make from injecting 780 into the fibre is also around 520 nanometers. And so, to show you, here's the spectrum of these various colours here. And you can see that if I take the third harmonic of the laser, which is the blue thing, and I look at the weird green output from this fibre that comes from a spectrally shifted version of the 780, those two overlap. But the mechanism by which they got to that wavelength was quite different. And so that allows us to actually obtain this offset frequency without needing a whole octave, because we look at the shift between those two spectra to obtain that. So we've done that and stabilised the whole laser. And so essentially in one step with a commercial laser you can basically replicate everything else. What did we use that for? Well, we basically recently took it to the Anglo-Australian telescope, which is a little bit south of here, probably 500 kilometres south of here on the top of the mountain, and we injected our frequency comb into their ultra-high resolution spectrograph, and we took a short 20-second exposure on the CCD, and you can see all of these sticks, which represent actually resolving our frequency comb itself. And then we also injected in there what they standardly use as their calibration source for their high-resolution spectrograph, which they use to look at things like redshifts and all of that sort of jazz. And in fact, to do really exciting experiments like look at quasars in the far distant space to see whether the spectral lines have shifted in ways that you can't explain, which might suggest that there are changes in the fundamental constants. So anyway, this is their spectrum using a 130-minute exposure. This is a 20-second exposure, and they get these two very weak lines. So if you look at the cross-section, you can see this is the spectrum they use. Clearly, having this infinity of lines lets you do a fast calibration, and you can also check linearity, which you couldn't do with these systems. So that's a realistic hope for fixing up these, and it turns out that the calibration of the spectrograph is the limit, one of the limits at the moment in basically looking for constant drift. Obviously you can go and buy one of these frequency combs, so what was the Nobel Prize in 2005 is now a realistic prospect. If you've got €300,000 to spare, you can go and buy one of these devices now. Okay, well, I think we've reached a stage where we've now looked at noise and modulation theory. We've also looked at how we can compare two different clock and a sensor, or two clocks using our frequency comb technology. So we've got the sort of background knowledge for the measurement technique. We've also got the knowledge for characterising various oscillators. So I think we've reached the stage where we're actually going to start to look at some clocks. And the first type we're going to look at today is essentially where we've taken a laser and locked it to a macroscopic oscillator, something that essentially is going to cause the output of our laser to map back onto itself. And this is something called like a macroscopic oscillator, you might like to term it. And tomorrow we'll look at atomic clocks, so where we're going to stabilise a laser by comparing it to some sort of resonance in a quantum system. And I like to sort of break them up into these two sort of categories where typically if you try and look into quantum absorbers, you're always signal to noise limited. You always don't have enough photons. And in that circumstance, you tend to have a pretty low signal to noise, and so that means you're dominated by fast frequency fluctuations in that case, because you've got less signal in the short term. And so you tend to see an output spectrum that's got a lot of width. But the central frequency of this is very, very well defined. So if you remember back to my target that we started on the third slide, this is really an accurate but imprecise clock. On the other hand, this is the first ones we're going to look at, which is stabilisation to some macroscopic oscillator where you usually aren't photon starved. So it means you've got great signal to noise, but the actual cavity itself is subject to thermal and environmental fluctuations which result in the frequency jittering around. Okay, so here's my broken into a table, these two types of clocks and oscillators, if you like. There are these sort of macro types, which we're going to talk about right now, which range in size from sort of microns up to metres or hundreds of metres in some case, and you've got tons and tons of photons. And so the advantage of this technique is it's got lots and lots of signal to noise, and it's also tunable. The disadvantage is that they're sensitive to environmental fluctuations. The quantum things which we'll talk about tomorrow, at least this class, to do with neutral atoms, and unfortunately we don't have time to talk about ion clocks, so I have to leave that for some other time. You know, you've got something like 1,000 to 10 million atoms usually involved in the story, and you end up with much fewer photons in order to detect whether your laser's in resonance with these atoms. And so you really got you're in this medium signal to noise ratio. The advantage is that you've got lots and lots of stability. The ion clocks, on the other hand, tend to eliminate even more environmental influences than the neutral atom clocks, and so they potentially got the ultimate accuracy for defining a second in the future. Okay, so here's some pictures of macro resonators showing various sizes. Here's a sort of conventional Fibre resonator, which is some sort of block of glass or crystal that's had a hole drilled in the middle and we fused mirrors on the end of it. But there are also these other type of small microspheres which you make by melting bits of optical fibre. We use micro machining to make these discs, and we'll talk a little bit about the first and last of those categories as we go through here. So how do we go about making this thing useful? So we take a laser and we inject it into our Fibre cavity with a couple of mirrors on the end, and if we monitor the transmission, the optical transmission through this fibre as we tune the frequency of this laser, we end up with some sort of usually Lorentzian shaped absorption feature. Oh, actually we're monitoring the reflection in my picture here, not the transmission, so you've got to imagine we're going to detect a little bit of the reflected light. So we see a less absorption when we move to this resonant condition. What's this resonant condition? That's the condition in which there's a whole number of half wavelengths between these two mirrors. Essentially, we're in the constructive interference between these two high reflectivity mirrors that are bonded onto either end there. And the defining factor, there's really two defining factors to the quality of this resonance. The first is what's its width. You usually want a narrow width, and that's defined by this thing called the quality factor, so that's the central frequency divided by its width. The other defining factor is how deep it is, which is something that's usually left out in the textbooks, but is really a real matter of experimental concern. You need to worry about how deep the resonance is as well. It's really the product of those two things that determine how well the system works. So how does one make this whole thing useful? How do you actually make the laser frequency lock onto the eigenmodes of this structure over here? Well, what we do is we take the reflected light and let it fall on the photodiode. And typically what we do is we have some sort of modulator here which can either modulate the phase or the frequency of the laser. And we basically do a synchronous detection between the reflected light and the modulating signal, and then use the error signal that's evolved out of this mixer to change the laser. So for those who already know that, then that's probably enough to say that. For those who haven't come across this idea, which is called the Pound-Griever Hall technique, and the Hall is the same guy who won the Nobel Prize for the frequency combs. And Ron Griever, in fact, is one of the other guys at that beer table, who's the D in here. Here it is in a more graphical way, and hopefully that makes more sense. So let's imagine we're modulating this laser frequency backwards and forward, and so this is my blue curve over here. And what we see on our reflected photodiode is we see some sinusoidal modulation that's a result of this frequency modulation here. And when we do it on the left side or the right side at the same distance from the resonance, we'll see the same response on the photodiode, but the phase will be opposite, because when the frequency is high here, the reflected amplitude will be high, and on this side it will be low. So we have a phase split between those two sides. And of course, if I did it further out, I mean here, if I do it further out, we'll have less signal. And if we do it right on the centre, for example, then there's something that's a little bit tricky, which is that if I modulate backwards and forwards here, and we consider what's the amplitude response from that, well, there's lots of it. But it turns out it's actually at the second harmonic of this signal, because of course we pass through the maximum twice per cycle. So if you ask how much of this fundamental frequency there is when we're on the centre of resonance, essentially we're detecting the derivative of this via this technique, then there's none. So if we do a detection in the amplitude of that single modulation frequency component, then I can draw some sort of red curve like this, which is 0 in the centre, and it's large on one side, it's, large in magnitude, but the opposite side on this side. So this is the perfect error curve, so I can use that to steer my laser to hold it on the centre of resonance. Well, how well can you do that? Let's do a little naive calculation. So this is the sort of typical, sort of hand-waving argument for how well you can do. And essentially, what we're going to do is we worry about how narrow is this resonance and how deep is it. And and then how many photons we're throwing at it. And we realised that there's going to be a fundamental shock noise limit associated with the finite number of photons, which is going to something like the square root of the number of photons here. So we've got some scaling factor here which reflects the narrowness and the depth. This C is for the contrast and resonance. And if you're whacking some reasonable numbers, like for a typical state-of-the-art cavity, the Q is something like 10 to the 10, and you might throw 1 milliwatt at it. And let's, I think we paid a bunch of money and we got a 100% cavity, which is within a factor of 2 of reality. Then you think that the fractional frequency fluctuations, or the Allen variance, as we've seen previously, could be something like parts in 10 to the 18, which would be pretty impressive. And for the experimental situation I'm going to show you on the next slide, even in that case, it's something like 5 parts in 10 to the 16, with worse characteristics that apply to the next system. Well, has anybody done this? Has anybody made a laser stabilised to a cavity with parts in 10 to the 18? The answer is no, they haven't. And the reason why is because these cavities are subject to vibration and also to this thing called fundamental thermal noise, which I'm going to tell you about in the next few slides, if you haven't come across them before. And once again, I can show you this slide, which I showed you previously, which is us locking a laser to a cavity, and you can see that in fact the fundamental shock noise limit's down here, something like just an order of magnitude under where we actually got to. So it's not bad, you can get within an order of magnitude of the shock noise limit, but in this particular cavity, what would I say, the parameters aren't so great, and so it's easier to get near the quantum limit than it would be if you really bought a state-of-the-art cavity. It shows you can get, like, not so far away from the quantum noise, and people have got to the quantum noise in limited frequency domains, but not everywhere. So let's talk about why it doesn't work as well as you would hope. And so one of these reasons is technical, and people have found a solution to this, which I think is pretty cool in the last couple of years. And this is so the first one is vibration. The problem is the cavities are subject to vibration, which changes their length and therefore changes the frequency. So even if you locked perfectly well to the cavity, you still suffer fluctuations because the cavity itself fluctuates around. And the second one is this thermal noise, which is fundamental and very hard to get rid of, which we'll talk about in another couple of slides. So the challenge is, how do you make these cavities completely immune to acceleration? And essentially there's been this sort of fantastic idea in the last couple of years that if you cut the right shape in these cavities, you can actually make them utterly independent of acceleration in all dimensions. And so basically the challenge comes down to making the right shape. And the sort of current technique is to go something like this shape, where you cut little flats so that the spacer has got this weird keyhole shape, and then support the cavity on these flats. And so I'm going to give you a little plausibility as to why that even works. Plausibility argument for why that works. Let's think of this as my spacer with my mirrors fused on the end, and imagine if I supported it on a platform underneath and we vertically accelerated it. Well, if we vertically accelerate it, it's going to squish down and spread out, and so the length will increase. But if I hung it from the top face of the cavity and vertically accelerated it, then the thing's going to stretch out and shrink, and so it gets shorter. So it might occur to you, and obviously it did occur to these smart people, that if we support the cavity from somewhere like its midplane and we accelerate it vertically, since this makes it longer and this makes it shorter, there's got to be some place in the middle where we can hang it and everything will be good. And so, you can imagine some picture like this. We hang it from this midplane, which is the purpose of those cuts, essentially, and we'll see some squish and stretch, and the important part was the distance between the centres of those two mirrors will remain unchanged. And you can do something more complicated with finite elements, and if you could read this scale, you'd see that in our particular case, we built one of these systems that the middle of the mirror is essentially unchanged when we do a vertical acceleration, and you can calculate from where you need to support the system. So we built one of these things. Here's our cavity. We mounted it up inside like a little chamber, which is to prevent temperature fluctuations getting in. And supported on some little balls that you can see there, some little rubber balls. And then that whole thing is mounted inside the vacuum system. And then we measured its vibration sensitivity. I'll present that to you, along with a lot of other people's results so far. So if you do absolutely nothing to eliminate the sensitivity to vibration, then you've got typically up here at something like 200 kilohertz for each metre per second squared. And so remember, we want to stabilise down to the hertz. So you need to do a pretty good job of eliminating this vibration sensitivity. And then after the original, Mark Knopcut, who was also from UWA, but is now at Giller in 2005, along with John Hall, that same name again, who won the Nobel Prize, came up with this idea to start with. There's been a whole profusion of work, and people are getting down to levels of something like 100 to 1,000 times suppression of the fluctuations to vibration. So if you mount that now on a vibration isolation table, essentially you can forget about vibration being a problem anymore. And so then you're left with this last problem. If you eliminate temperature and vibration and all the other technical things, you end up stuck with this issue here, which is the so-called thermal noise issue. So this turns out to be the case that, all materials suffer from Brownian motion, and you would expect, if you do a naive calculation for the level of Brownian noise due to the fact that the atoms themselves have a finite temperature, and then you average over the size of the beam, you would think that the length of the cavity is perfectly stable, but that's a problem at the level of parts in 10 to the 22. But if you do a more sophisticated analysis, it turns out that because at low frequencies, there's a lot of dissipation in these structures, in real materials that are made up of mirrors glued onto spaces and coatings. And it turns out there's a lot more mechanical dissipation, which leads to more fluctuation at low frequencies, which is exactly what we're trying to operate. Not only that, it also turns out there's another type of noise, a fundamental noise called thermoelastic noise. So just as there are fundamental volume fluctuations due to the motion of the atoms, there's also fundamental temperature fluctuations in small parts of the material as well. And if your material has a finite coefficient of thermal expansion, then that actually leads to further fluctuations as well. This was all realised by this guy named Marta. He's on here, and so he plotted up a whole bunch of frequency standards that exist in different frequency domains, and we looked at the frequency spectrum, and they all lie on this line, this 1 over F line, which corresponds, in fact, to the calculation which runs through there, the red line, apart from some vibration noise over here. So this fundamental thermal noise. And so it's a really serious problem. I mean, at something like a millihertz, it leads to hertz level fluctuations, and that's where everyone is stuck at the moment. And as we'll see tomorrow when we talk about atomic clocks, this is the actual limitation of atomic clocks as well, because it turns out you need to have one of these lasers locked to a cavity to actually interrogate the atoms. So, how can you lower this noise? Well, you're sort of left with three options. One, you can make a much longer cavity, because this is a fluctuation at the surface of your mirrors, and so as you make your cavity longer, then the fractional effect of those fluctuations gets less and less. But once you make your cavity really long, it gets sloppy, so you don't want to do that. You can lower the temperature down to 0 Kelvin if you want to. That's actually the approach that we're taking, but that's a pretty brute force way to go about it. And the other possibility is to start building the cavity and the mirrors and the coatings out of materials which have much less acoustic loss. And so you might think of things like sapphire or other crystalline materials which have very low acoustic loss, and that results in them also having low levels of fluctuations as a result of that low level of acoustic loss. And there's also work going on in Germany that I found out recently using technology that's essentially designed for building laser diodes, like VCSEL technology, to build little cavities in microfabrication techniques like that, because they have much lower acoustic losses when they're crystalline, and the acoustic properties of the coatings are much better matched to the substrates. So people are doing a lot of work like that to solve this problem, which afflicts gravity wave detectors and other high precision measurements where we want to use a Fibre cavity, such as like atomic clocks. And I wanted to tell you one application of these Fibre Pros, which is pretty fantastic. So this is the group of Achim Peters in Berlin. I took this image off their website. There's another group led by Stefan Schiller in Düsseldorf is doing a similar sort of thing. So this is a modern version of a Michelson-Morley experiment. So you remember Michelson-Morley was essentially designed to test whether the speed of light was the same in all reference frames. And so their idea is to basically set up two Fibre cavities orthogonally in this big block of ULE material, and they fuse some high reflectivity mirrors, so that's essentially two crossed Fibre cavities, and they essentially lock a laser to both, and then look for frequency differences that occur between those two cavities, synchronous with the orientation of that cavity. So as they rotate that cavity in space, and therefore change its orientation with respect to the Earth's motion through the universe, they look for a change in the apparent resonant frequency, which they would argue reflects the change in the speed of light in those two directions. So that's a modern version of a Michelson-Morley experiment, which obviously would be very exciting. So, and in our lab we're doing the same thing, but it's not me, it's other guy, Mike Fibre, who's doing it with microwave cavities, so he's got the same sort of thing, but with microwave resonators, but who cares, it's all the same, it's all photons anyway. So he's got a resonator pointing this way and that way, and the advantage of telling you about this is I've got a nice video that shows the experiment in action. So essentially we're going to rotate the experiment so that we rotate the orientation of the cavities with respect to the Earth's velocity, and then search for a change in the apparent resonant frequency of those cavities. So here's the guy Paul Stanix, who's putting the experiment together. The whole thing runs at cryogenic temperatures, so it needs liquid helium to be so that's the liquid helium, well, the gaseous helium at temperatures. So we're going to wait till it builds to a crescendo. Checking it out. This is real experimental physics. So this is the experiment in reality. So down the bottom here is a liquid helium duo with two of those oscillators pointing orthogonally, and this thing rotated around for a year. In fact, 2 years in total in the end. And all of this electronics up here runs the two oscillators. And so if you see the film from up in Peter's lab, it looks very, very similar, except it's got lasers and cavities. We're not worried about that. So what are we expecting to see? So what we're expecting to see is something like this, that if we look at the frequency spectral density, then, and it's being rotated, in this case it's something like, every 6 seconds it rotates, and so due to vibration and noise, there's a bright line and 6 seconds of fluctuation. But what we're hoping to see is that just on either side of this line, at a frequency separated from that line by 1 over 1 day, we should see a little modulation stick. Just as I talked about in the first lecture about the modulations ending up putting sticks on the side of those carriers. And that modulation would indicate that the frequency is being synchronously changed with the day on top of the rotation of the device as well. So it's like a double modulation. And if that was to be the case, if you saw some little sticks there, then there'd be a Nobel Prize at the offing and everybody would be excited because we'd have found that Einstein was wrong and the speed of light wasn't constant in every reference frame. What happens in reality is that as time goes by, the measurements just improve and improve down to the level of, so this is the group of, so these are the Dusseldorf group, the Berlin group and the UWA group, which, so I'm presenting this in terms of if there really was an ether, for example, like some sort of preferred reference frame, then you can basically set a number on how fast we must be moving through that ether. So the Michelson-Morley experiment was down at the sort of few meters per second level if there was an ether. The precision of the measurement's now down at, whatever that is, 100th of a micron per second. So if there is an ether, we're moving through it very, very slowly. So I think I've got a final slide. And we're finished. So the other exciting thing I wanted to flag for you is one example of the use of these microscopic cavities. So if you launch light into these microfabricated rings, which are also a way of confining light so it circulates around here. And if the Q factor is high enough, and so in this case it's something like 10 to the 8th on this work that's been done in the group of Tobias Kippenberg, you can actually concentrate the light to such an extent that you get strong nonlinear properties, just as we saw in the optical fibre that I started the story off with for this second lecture. And normally, nonlinearities are really annoying things to have because nonlinearities cause frequency instability. But in this case, Tobias's group is actually utilising that nonlinearity to actually generate a frequency cone. So by injecting in a continuous wave signal here, the nonlinearities are such that the instability actually turns the output into a pulsing output. And this pulsing output, if you looked in the spectral domain, looks like a cone of frequencies. And our preliminary results seem to show that this cone has got as good stability as the fibre or titanium sapphire cones that we started the story off at. Except that this whole thing's like a cone on a chip. And so maybe this is the way forward in the not too distant future, where essentially we can pack all of the technology that allows us to build things like spectrum analyzers and oscilloscopes for RF technology, but do it all in the optical domain by utilising this sort of microfabricated frequency cones and the small little frequency standards as well. So thanks for that, and see you again tomorrow.
So you have seen the talk that Kagome gave about those cavities that were on the later slide.
Oh, there we go.
So everything goes together here. So the technology is here, and this is this as well. So.
Like that.
Questions to Andre? Alex?
That last slide you put up,
Yep.
you said, I presume you're talking about a toroid and not a microscope.
Sorry, maybe, yeah.
Yeah,
Sorry.
it's just at the title. So with that toroid,
Yep.
you don't get a full octave in the frequency.
No.
So you couldn't use it as a pump.
Well, except that, as I showed you in our fibre frequency cone, in fact, there's not a full octave there either. In fact, it's only 10 nanometres wide. But by using this spectral shifting technique in the optical fibre, you can still generate an offset frequency without needing a full octave. So there seems to be ways around that. I mean, the problem there is that the output power is extremely low, so you're not going to have enough to drive one of those fibres. But I mean, you could put an amplifier there, perhaps, or something.
Any other questions, Andre? When you were showing those wonderful colours in your fibre,
Yeah.
there was so much nicking up that the efficiency of those fibres must be very, very low.
No, the efficiency is really high. It's just that your eye or a camera is an incredibly sensitive device. So, I mean, your eye responds to the peak power in some way. And so you see this real intense brightness, but actually there's nothing there. So, I mean, if you see what comes out the end, it hurts your eyes, the brightness of the colours. This is 100 milliwatts of total power.